I'm Brian Rexroad, and let's jump right into it. And I guess we're always talking about manipulation of code and things like this. Who would have thought just flipping a bit could make the difference, right?
Wow. This one is particularly fascinating to me. This it's an attack they're calling the Rowhammer bug.
All right.
Now this the Google Project Zero team just released an advisory about this, and they're building off of work done by researchers at Carnegie Mellon and Intel Labs. The idea behind this is that there's physical effects within memory, in particular DDR3 DRAM chips, where when you read from memory, it can cause slight disturbances in adjoining memory because the scale at which you're operating is so small that you start having these weird electrical leaking effects around them. So the idea of row hammering is basically reading from memory adjacent to memory you'd like to influence repeatedly to see if you can actually cause bits to flip. Now it seems that they found a way to fairly well repeatedly do this and chain it into an actual exploit against different platforms. They come up with 2 exploits. So the first one is against Google's native client, which is basically a way that Chrome can run native code, like x86, much faster. So it behaves almost like an x86 processor in a program. And it's got its own sandbox, so to prevent sort of the regular kinds of attacks you would expect, turns out they found a way to bypass that sandbox using some really clever modifications to jump calls in memory, relying on those bit flips to actually change a jump call from one location to another one outside of bounds of what the sandbox would normally expect, and there you go, now you're outside of the sandbox. The second one is against just a Linux kernel, and it seems that you can modify the page table entries, which is basically, I don't know how our viewers know, if they know about virtual memory, physical memory, but basically you're modifying where the computer expects to find different memory locations. So you can give the program control over its own page table, and then it gets to find where it gets to call. And then it's pretty much game over. So, I mean, this is, I find it most cool because this is physical, this is physics causing exploitation of software.
Yeah, there are a lot of things about this that I guess I can relate to a little bit. First of all, it's really kind of very similar to sort of a buffer overflow type of attack, where you're trying to inject code in a place where you didn't expect it to be, right? So sort of jump to a new place, you're basically flipping a bit so it changes where a jump goes to. It's very similar to what a buffer overflow is trying to do as well. Try to get something so it's jump into a place where it's executing code that it otherwise would not have executed, right? And one of the things I find very interesting about, you mentioned the electrical effects. That's really, as you said, the geometries of the memory elements are getting so much smaller, and really a DRAM's just a little capacitor. It's just a little place where you store a charge. When you go to read that thing, you're just measuring just a few electrons. I'm not sure about the number at this point, but it's it's like handfuls of electrons that they're basically stored in that capacitor, and to decide whether it's a 1 or 0. So if you can, based on the proximity of those, get some of those injected into a neighboring memory cell, there's a possibility of getting that type of an error to occur. And it's really a kind of a cool thing. We were talking about earlier how memory checking, the error correction codes, were actually reintroduced, I think on the order of maybe about 10 years ago. They had basically gotten rid of them, but years ago they used to have those, and it was partly because the memory elements were actually encased in, or the chips were encased in ceramic, and the ceramic had some radioactivity associated with it, and so a little, alpha particle or something could get in there and actually change what the memory was. And so in order to protect against that, they'd have a parity bit to see if there was an error or something. They didn't have the correction, but at least the parity associated with it. Very cool stuff.
Yeah.
And so what do you think? Is this something we need to be really concerned about right now?
I think it just came out as of today's taping, and they've provided not exploit code but test code to show to determine whether or not the memory modules that are in your machine are susceptible to these bit flips. Now, they've tested about, I want to say, around 30 different combinations of vendor and memory, and it's not clear that this is a huge widespread problem. There may be certain platforms that have to be worried about. DDR4 is not susceptible to this. Memory with ECC is less susceptible. There's still a chance that if you manage to flip more than one bit, that the ECC is not going to be able to compensate for that, because I think it only really checks for
the probability.
parity,
Yeah, the probability of being able to detect it goes down as the number of bits goes up, but it's still, I'm not sure if they use 1 bit or multiple bits associated with that, but it's...
Did they say why DDR4 is not susceptible versus DDR3? What is it about DDR3? Is it something about the physical aspects of it? That
I'm not really clear on that myself. All I know is that somehow DDR4 is able to compensate against this.
Okay.
I'd be interested to find out the actual reason.
Yeah, I was wondering if somebody knew about it and maybe they engineered that in or something, but I don't know.
There's a possibility their correction coding is stronger. Again, as geometries continue to get smaller, they're putting more protections in place for this kind of thing, this eventuality. You know, actually in disk drives, they've done something very similar, added error correction coding that didn't exist previously because the geometries are getting so much smaller, and you'd expect that there's going to be some probability of, you know, some sort of an error. And it kind of brings to mind our own minds. You know, they're, you know, one of the, I guess, the most complex computing platform that exists, but it has errors all the time. You know, there are just so many things going on that they get jumbled up. And I think this is just that, you know, that next step in the evolution of things, where things, you know, you have to build in tolerance for errors as a part of the platform. And this is a case where they've demonstrated how it could potentially be used for malicious purposes, mind manipulation.
Well, being a software developer, you should always code in for the possibility of errors into your code to check for unexpected,
that's true too.
Well,
you know, things to occur.
The question would be, do we have to start coding to protect against errors in our own hardware at this point?
Oh,
I mean, do you have to double validate everything you've saved to memory when you pull it back out is really what you'd save to memory in the
well,
first
I
place?
guess within reason, right? You don't want to sacrifice performance too much, you know, to have a perfect situation with your error correction, but you know, to some degree, I would say
you should be able to rely on the hardware. I mean, it's in fact, I mean, ultimately, you want to be able to trust what's coming out of it. Otherwise, what can you trust? That's really.
Well, I mean, I would put that at the hardware level. That kind of like, you know, the firmware or something would be checking for whether there's an error. Not in my software would I be not trusting the memory that's in my machine. I wouldn't, you know, if I'm writing something in Java or whatever. But you know, in general, I'm just saying code in general should always have error checking for whatever it's doing with its own stuff.
Yeah.
There's one more parallel that I thought was kind of interesting. Single bit flips. There was research done a couple years back on single bit flips in DNS. I don't know if you remember that one, but it turns out that, you know, if you take a popular domain and occasionally somewhere along the transmission line, a bit will be flipped when a DNS request and it becomes like Foogle.com instead of Google. If you go ahead and you register Foogle.com, you will get a significant amount of traffic that's destined for that other domain. And there's really not much to be done for that. I mean, you can set up your own little traffic collector, and simply because of a single bit, you're going to start getting significant.
Yeah, it's actually an interesting one, because the likelihood of getting a bit error in transmission where it's gone through a lot of systems along the way is greater. In fact, the whole, you know, IP network, internet, is based on sort of a best effort delivery activity with the expectation that some of those packets aren't really going to get there without some kind of a munging. But DNS uses UDP. It doesn't have the, it has some header error checks, but it doesn't necessarily validate that the packet itself that's left to the end system, and I don't think DNS did a whole lot to make sure that it got delivered without some.
And again, that's a performance reason probably. You know, that's why they use UDP.
Yeah, absolutely.
Completely for performance aspects.
Yeah. So that's why we overlay it with SSL certificates to make sure that we're talking to who we think we're talking to, and that the domains match up, and then ultimately put encryption on top of that, which it helps to maintain the integrity. You pay for it in performance. That's right. It's there's no free lunch.